Hi. This is a continuation of the history and discussion of the Moore's Law of AI from last year. And what I'm going to try to do is cover what's happened since last year. The first thing I want to do, however, is discuss something that should have been discussed last year, and this is Wave to Vect 2.0. This came out just before the course started in the summer before the course started last year. And this is a system that learns to transcribe audio, speech signals, into symbol sequences with no labeled data, no labeled speech to text translation. It's just listening to audio and generating sequences of symbols. And this is analogous to what a child does when they learn the phonetics of a language before they learn the words or how to speak. So this is trained on 53 hours of unlabeled audio. It learns to convert that audio into a sequence of these units they call pseudo-text units. They're not necessarily what we would call the phonemes of the language, but it does learn automatically to translate speech into symbol sequences. Then what you can do is take this speech to symbol sequence system, and instead of learning speech recognition directly from audio, now you can learn speech recognition from the symbol sequence that this pre-trained language model generates. And that turns out to be a much easier problem in the sense that it requires much less data. So once you've trained on 53,000 hours of just raw speech and have this speech to symbol sequence system, you can then take only 1 hour of actually transcribed speech and learn to map those symbol sequences into text to do speech recognition. And what happens is with 1 hour of labeled data, you get a system that outperforms the previous state of the art on 100 hours of data. So you've got 100 to 1 compression in the amount of data, the so-called data complexity it takes to learn speech recognition. So this is a significant advance in the use of raw speech, unsupervised or self-supervised data. We'll be talking about how this is done in more detail later in the class. Okay, this came out after the class last year. This is a generative spoken language model. So a language model, like this big event of GPT-3 last year, is something that takes text, a sequence of words, and predicts the next word. And then what you can do is you can type in a prompt and ask the system to continue generating text from that prompt. And that's how GPT-3 generated some blog post that fooled lots of people. Here, what we're going to do is we're going to take audio, just audio, and we're going to learn a model of audio sounds, no text at all. We're not going to do text at all ever here. So what we do is we take the previous system or something like it to train on audio and turn audio into a sequence of symbols. Then we use a language model, which can take any corpus of sequences of symbols to predict the next symbol in this symbol sequence. And then we construct a generator that will take the symbol sequence back to sound. So we're never going through text. We're going sound to sound, trained only on sound. So this is a generative spoken language model, a language model. And it's fun to listen to this. So let me see if I can do this. I want to share sound. Here we go. Okay, so what we're going to hear now is one prompt followed by automatically continued in the style of a language model, but directly in sound.
When an aristocracy carries on the public affairs, its
verification there may be in science, the connections of the valley to which it was called upon to lecture, conferring on similar descriptions of opinion, and in other instances which appear to have never exceeded the same results. It cannot be found that the notion of the most ideal opinion is the popular notion of the edifice, nor is the susceptible possibility of introducing the same state of the continental character. The scope of the theory of the notion of the when an aristocracy carries on the public affairs, it's coming to the chronicles of the public jurisprudence as to what is observable, not naturally demanded of it, by the way in which postal axes are adequate delayed by freemen, and especially kindering the same stock. No body of postal acts has ever been demanded to labor, and any stock was personally adequate to labor. End of section 19. When an aristocracy carries on the public affairs, its taste of a grading makes up a precedent, and such as the aristocracy of past correspondence. The past correspondence has not been accounted, and the capital is reckoned under the apparent estimate of a capitalist industrial population governing the public population. For aristocracy is valuable to the public acceptance of this kind, for having nobodies to sympathize with it, and when a capitalist is within 20 years old, the population is said.
Let me get back. Okay, so if you could parse that, you're doing better than me. What's fascinating about this is it is sort of grammatically coherent, and what's even more interesting is that it's getting the prosody. It has a good model of prosody. Variations in duration and pitch and emphasis are plausible, right? They're actually modeling the statistics of those things in speech, which you're never going to get that out of a text-based language model. So again, I think this qualifies as a significant development. Okay, the next thing I want to talk about is something that came out in January, contrastive language image pre-training. So this is trained on images associated with text. So I can take off the web, I can get captions for images, and that gives me images paired with text. And I can, another thing you can do is you can take hypertext links to pictures, and you've got the text of the link and the picture, and that's another way of associating text with pictures. But you find some way of associating with text with pictures, and then you take a huge corpus of these pairs, and you train it to try to, what we're going to do is we're going to train it such that you give it the image, and it has a generative model of the text that would be associated with that image. So it's like a conditional language model. It's going to generate text from an image. So one thing it can be used for is just image captioning. But what makes this exciting is not so much that, but you've trained it on this naturally occurring pairing of images with text. Only that. You haven't trained it on ImageNet class labels or any other kind of human labeled data. And then you can show that this thing can be made to do classification. And the way you do classification with this model is you design a prompt to see if this is a picture of a dog, for example. So you want to know, is this a picture of a dog? You show it the picture, and then you say, what's the probability of the sentence, this is a picture of a dog? And you compare that with the probability of the sentence, this is a picture of an apricot, or whatever your class label is. And what that lets you do is simply by designing what your prompt is, what's most likely when the picture is a picture of a dog. This is now called prompt engineering. By designing this prompt, you can build a classifier. So here's an example of classifying food. So you give it this picture, and then you compare the probability that the language model conditioned on this picture assigns to these different sentences. So a photo of guacamole, a type of food. And that has much higher probability, according to the language model, than a photo of, I don't know how to pronounce that, ceviche, a type of food. And so you can solve classification problems. And what's interesting about this is it's not trained on any particular data set. So it's just trained on a corpus of image text pairs. So it generalizes much better than ImageNet trained classifiers. So this is a bunch of data sets. This is, I take the ResNet model trained on ImageNet. So this is an image model trained on ImageNet. And then I try to use these features to classify in other areas. So I'm shifting the problem into these weird other domains, and the ImageNet classifier pretty much falls down, right? When you get to these ImageNet adversarial, it's at 2.7%. However, this CLIP classifier with prompt engineering maintains strong performance across all the tasks. So that's the idea behind CLIP. So this is generating text from images. Okay, here's something that came out at the same time. These are both OpenAI developments. The speech, I should have mentioned that the speech work was Facebook. Okay, this is again trained on pairs of image and text, but this time we're going to generate the image from the text. So now you give it some text and it generates an image. And DALL-E is this, DALL-E is not an acronym. Apparently it's just a combination of the surreal artist DALL-E and the Disney character WALL-E. I don't know, don't ask me. Okay, so you get this amazing stuff, right? An illustration of a baby daikon radish in a tutu walking a dog, and it does it. Shocking. And we'll be talking more about, the general learning principles that are happening here. Anyway, the learning that underlies this is fascinating, and we're going to get there. An armchair in the shape of an avocado, and it does it. It's just creepy. These are cherry picked, right? It doesn't always do this well. Okay, I'm going to end on one more. July, this sort of just happened. Well, this past summer. GPT-3, we've talked about a bunch. CodeX is a language model, again, another language model, except this time it's trained on code. So you take a large body of code from GitHub. They sort of took all the public GitHub code repositories and trained a language model on it. And these GitHub repositories have comments, right? They're full of not just, or text, they're full of text associated with code. So now, instead of images associated with captions or text, we're taking code associated with text, computer code. They actually initialize it with the GPT-3 language model. They initialize this text code model that way. What they say in the paper is that that's not necessary. They could train this model from scratch to perform just as well as with that initialization, but the training takes much longer. So the initialization speeds up the training. And this is underlying something called GitHub Copilot. On the course page, I'm going to put a link to a demo that I would encourage you to watch. Okay, so what this is going to do, it's associating code with text. So just like DALL-E generated images from text, this thing is going to generate code from English text. Now, it's not a great coder. It's not going to discover an algorithm that you just designed from some English specification. But what it's particularly good at is knowing a lot of languages and APIs for applications, because that's the kind of code it's read. This may, the application for this may be that it's a replacement for Stack Overflow when you don't know how to do X in language Y. They'll just say, code X where you say X in English, but it should be simple in language Y, or you give it again, there's a lot of prompt engineering that's going to go on here. You have to give it the right prompt to get the code that you want in the language that you want. And it will show you code in that language that's correct for that language, because you can sort of run it through. You're going to filter it by the Copilot's going to filter it by some compiler or something to make sure this is a reasonable thing. And you may be able to look at that code and then know what to do, right? It's my intuition is that it will ultimately sort of replace Stack Overflow for how do you do X and Y. It's good enough at rendering English into code or into machinable, machine actions, that I also suspect this is going to strongly influence or perhaps even replace voice assistants like Siri in your devices. So this is a big deal, right? I mean, the idea that you could do automatic programming from English has been a fantasy of AI for a long time. It's not yet clear exactly how far this has taken us or how far this will go, but it certainly attracted a lot of attention. And it's kind of creepy. And I would encourage you to look at just search on CodeX demo. So I just want to end this unit on a sort of a high level note. So it's clear over the last decade that particular advances in machine learning generalize across many domains. So there are all kinds of ideas, RNNs, ResNet, everything we're going to be doing in this course, the fundamentals of deep learning, seems to be extremely general. And when we ask the question, is there a Moore's law of AI? We can sort of ask it two ways. One is, what's happening in the applications? Are the programs getting stronger? Are we able to do new things that we weren't able to do before? Which is one spirit of that question. The other spirit of that question is, are we understanding fundamental principles of learning better? Are we making fundamental advances year to year, significant advances year to year in our understanding of general principles of machine learning? And those are sort of two different interpretations of this question. Is there a Moore's law? And this course is, and me personally, I'm very interested in this question of our rate of advance in fundamental understanding. So we're going to take that perspective. It's certainly true that the last decade has seen many steps in our advances in our understanding of the fundamental domain-independent learning mechanisms, or at least we found a lot of powerful domain-independent learning mechanisms in the last 10 years, many new ones. So I'll leave it there, and most of the units will be recordings from last year, but I will modify and update various units as we go. So thank you.